Hello everyone. Today we will make an experiment to measure distances with the component LDR. To measure distances, we will use the property of LDR that if you change the light intensity of a light source that is seen by the LDR, it changes. So now let's start with the step 1. In this step, we have a resistor, we have a DC source, and we have an LDR. You should connect them in series, and now you see the voltage value of the resistor here, and as you can see it is 0.6, and now I will change the light intensity. Firstly, it's like that. As you can see, I am showing the light to the LDR, and voltage actually increases. And if I increase it, it increases more to the voltage of the resistor changes, and it increases when I increase the light intensity. And if I take it, as you can see, it decreases. And if I make it dark for the LDR, it decreases more. To understand this, you can make use of KVL rule and the LDR's property, LDR's actually specifications. And now let's move to step 2. In step 2, again we will have an LDR, but this time let's make it out off. This time we don't have a resistance, and we will try to understand the resistance change with the changing lights of the LDR. In multimeter, we make it on. As you can see, it's now approximately 108 kilo ohms, and I will change the light on the LDR component. And as you can see, when I get light, the resistance value decreases. And if I take it, as you can see, it again increased, but it has an, as you can see, if I make it like this, the resistance increase. Now it is not as much high as when I make it dark, because there is an ambient light in our lab, and our challenge is that although there is a ambient light in this environment, we will try to measure it, measure the distance more accurately. Now let's move to step 3. In step 3, this time we will change the light intensity of the light source, and that's in step 2 we changed the distance, and we have seen that when it's close to the LDR, when the light source is close to the LDR, this resistance decreases. If I make it a bit long, the distance, it increases, the resistance value increases. And now I will, in step 3, I will keep the distance between the LDR and light source same, constant, and I will change the light intensity of the light source. Now I'm decreasing the light intensity, and when I decrease, as you can see in the screen here, I decrease a bit more. When I decrease, the resistance value, as expected, increases. And if I, the distance is same, as you can see, distance is same, distance is constant, but now I'm changing the light intensity. when I increase the light intensity, resistance decreases. Now, we are moving to the fourth step in our lab, and in this step we will make a calibration. As we stated before, we have an ambient light here, so our relation will be affected and we will have an intercept value. So we will try to find the relation between the resistance of the LDR and the distance in these conditions, and you need to do this in your conditions too, because of the ambient light and the specifications of the components. And now our system consists of a ruler here, as you can see, and a light source. It stays like that, and an LDR. We will move it and we will make measurements in some points, in some distinct points, and we will record them, and then we will have a trend line by using the Excel application. Now let's start with 4 centimeters. Okay. In 4 centimeters, our resistance value is 0.34 actually. And now I'm moving to 8 centimeter distance, and in 8 centimeter distance it is 0.59 actually. And now I'm moving to 12 centimeters. It is, let me keep it constant, and it is 0.85 actually. And now I'm moving to 15 centimeters. And in 15 centimeters, our resistance value is 101 kilo ohms. Yeah, 101 kilo ohms. And in 20 centimeters, our resistance value is 123, let's say. And I'm moving to 25 centimeter distance in my ruler, and our resistance value is 139, let's say, kilo ohms. Okay. And now I'm measuring 27 lastly, my last measurement, and it is 144 kilo ohms. If you pay attention to my measurements, I'm recording the distance in centimeters and the resistance in kilo ohms, because in real life examples we will have, actually generally we will have these type of distance and resistances. And I recorded the values, and now let's check the values here. As you can see here, our measurements, distance in centimeter scale and resistance in kilo ohm scale is here, and our measurements are here. As you can see, and as we know from physics and the properties of the LDR, the distance and the distance is x-axis, distance is in x-axis, and as you can see it is in centimeter scale, and sorry, our y value is the resistance value in it, and it is in kilo ohm scale. And as you can see, the relation between the resistance and the distance is logarithmic. We have a logarithmic equation here, and it goes like a logarithmic equation. Now, by using this equation, I will try to measure distances. And let me check my steps. Okay. Firstly, I need to record the formula to apply it, and our formula is like that. Resistance of L is 0.59, like that, and then distance minus, we check it, 0.5753. Okay, our formula is here, and with this formula I will try to, and this is the important part, I will make the system here constant, because if I change, our calibration values will change too. So let's make it. I will try firstly. Let's say 13 centimeters. It's up to you. And in 13 centimeters, I have 0.9. Let's say 0.89. Distance is 13 centimeters, and resistance of LDR is 0.89 kilo ohms. As you can see here. Now, I will place the distance to the formula. Let's make it times ln 13 minus 0.5753, and I have this value, and between this value and this value, of course, we have an error rate, because there is ambient light, and the measurements can have these type of error rates. But as you can see, let's try another point. If I try with, let's say, 21 centimeter distance, I have from multimeter, and I have 1025, which distance is 22 centimeters and 1025 kilo ohms. Now, I have my measurement values, and again now I will use the formula to obtain the same resistance times ln okay. As you can see, in 22 centimeters we have a lower error rate actually, and it is approximately the true value. Now we can conclude the experiment. We calibrated the LDR, and we used the property of LDR that this component resistance changes with light on it, and by making the calibration by measuring distinct points and obtaining the relation like that, as you can see here, we can measure distances with this system. Thank you for watching. That's all.